as a measure. And as a linear functional, mu has the following property: it is positive, and mu of 1 is 1. However, you see, what does it mean positive? As a linear functional on a star algebra, we say that mu is positive on the star algebra P if mu of any product of this form is greater or equal than 0. And we say that mu is a state if positive and normalized. Mu of the identity is the identity. But there is another very important notion of positivity for polynomials, which is pointwise positivity. A polynomial is a function from the real line to the complex numbers. So it makes sense to say that this function takes positive values. This is pointwise positivity. Okay? So the polynomial is, as a function, is positive in every point. The crucial lemma is that in dimension 1, pointwise positivity coincides with positivity in the star algebra sense. So, in other words, what does it mean? This follows from the fact, a simple lemma. I have put the proof, but I want to do, as I said, I would like to give you a conceptual overview. So the proof is written in my notes that I will give to you. But maybe I will try to arrive to more interesting things without losing time with showing you the proof. So this is very, so what does it mean, this lemma? This is equivalent to say that any polynomial, any positive, any pointwise positive polynomial in one variable is a sum of squares. In the famous 23 Hilbert problems, the 17th problem of Hilbert was, is it true that every rational function which is positive is a sum of squares? And this was solved by Artin. But the same a small variant of this problem is it true that every positive polynomial is a sum of squares? And this was solved negatively by Motzkin, who produced counterexamples. So the equivalence of pointwise positivity and positivity in the sense of a star algebra is typical on one dimension. We will come back on this point later. Okay, so I don't give the proof, but it is in one dimension is simple and is written in my notes. And incidentally, this is the first open problem I want to mention. Namely, what is the open problem? The open problem is that this is related to the famous Hamburger moment problem. The Hamburger moment problem in one dimension, moment theorem in one dimension, tells you that if you have a state on the polynomial algebra, then this states there exists a measure mu such that this state has this form. There may exist many, but one exists. In multi-dimension, because of this problem, the literature, there is not multidimensional Hamburger problem. So the first open problem I want to mention is this. Can we find a multidimensional version of Hamburger momentarily? We discussed with Rajab had some idea, and maybe we can do something, but we will come back on this point later on. Just let us continue our broad view. Now, so we have spoken of states on P and probability measures on R. And now we speak of states on P and scalar products on R. If we have, in fact, pre-scalar product. By a pre-scalar product, I mean a sesquilinear form, which is positive definite like usual scalar product, but it may be degenerate, so there may be vectors with zero norm, and I don't take completion. It will be clear why we need this more, I will insist during the course of why pre-Hilbert for dealing with polynomials is better than Hilbert. Now, given a probability measure, we give a state on the algebra of polynomials. Conversely, let us see, given a, if I have a state on the algebra of polynomial, I have a scalar product on the polynomials. Because I simply define, this can be done in any state, even in the non-commutative case, but we need only the commutative case. Now, we ask ourselves, so every state, a similar problem we measure. In the previous lemma that I mentioned, the Hamburger theorem, the Hamburger problem was, given a measure, I always have a state. The Hamburger problem was the converse. Given a state, when I have a measure. We can put the same problem for the scalar product. Given a state, we have a scalar product. Which scalar products come from a state? And what is interesting is this, that the following proposition is true. A scalar product, a pre-scalar product, because you see, you may have zero. Think that the measure mu can have, for example, support in a finite number of atoms. So a lot of polynomials will be zero for this measure. So now, a pre-scalar product which I denote like this, on the polynomial algebra P, comes from a measure more generally from a state, like the Hamburger theorem is the same, comes from a state, in the sense of this formula. Let me emphasize this. In this sense of this formula here. If and only if the scalar product, because the identity of P is the algebra of polynomial, so x to the power 0 is 1 by definition, so the constant function is equal to 1 is the identity of this algebra. So the norm of the identity is 1, and the second condition is interesting. X, Q, X, P, Q equal P, X. So you see, what does it mean? It means we know that X is real valued. Okay, and X is a Hermitian, that is I don't use a self-adjoint, because self-adjoint in Hilbert space theory has a technical meaning, which has to do with analysis. So I use a Hermitian, which is purely algebraic. So we know that in this scalar product, any real value, multiplication by any real valued function is Hermitian. But here we are given the scalar product. So what we are saying is that X, which is an Hermitian element of P, is also Hermitian with respect to the given scalar product. Okay?
X is the polynomial X, right?
Please?
X is the polynomial X, right?
No, X now is the single, X is a single random variable. However, since the single random variable and the P and Q can be arbitrary, then X can be any monomial. You simply prove by induction. This is very easy. You can do as an exercise. So if X is symmetric, X to the power, by the way, X, I will now, from now on, since this basis is fixed, I will use the notation that XE1 will be X. So the function that I defined in the beginning will be denoted by X without putting the basis, because we fixed the basis. I forgot to say that it's very trivial to check that while the function X depends on the choice of E1, the polynomial algebra doesn't depend. And this will remain true in finite language. This is one of the difficulties of infinite language. That under change of basis, the polynomial algebra doesn't, under linear change of basis, the polynomial algebra doesn't change. So it's intrinsic, doesn't depend on the choice of the basis. Okay, now, so X is this random, but it's this random, so thank you, because I forgot to specify that X was this notation. Okay, so if it is true for X, but PQ here are arbitrary polynomial, so it is also true for X to the power n, as you see very simply by induction. Okay, and therefore taking linear combination with real coefficient, any polynomial in X with real coefficients is self-adjoint. Okay? This is the necessary, essentially, this condition is obvious, because you see, if you put P and Q equal to 1, you have phi of 1, and the phi of 1 is equal to 1, because phi is a state. Now, so this is a necessary condition. So this is essentially simple condition. Here, you have to just use the fact that the adjoint in a pre-Hilbert space is uniquely defined up to addition of zero normal vectors. So essentially, if we call, you see, if we call, so essentially, what I say is this condition means that the adjoint, well, let me prove this. Take a linear combination and multiply it by a polynomial in the scalar product. Then you will have that this go out into the conjugate, and then you will have xj, p, and q. For what we said before, as j is a Hermitian, so I can bring on the other side p x power j of q, and you see now this is equal to p sum a conjugate j of xj, but this is exactly the adjoint in the star algebra sense. So this is p times the star adjoint of polynomial, sorry, but from this identity I have also that this is equal to the p times the scalar product adjoint of the polynomial, which I denote with the cross. And so you see that this adjoint and this adjoint differ by a zero norm operator.
What is the cross for?
Cross means by definition, if I have an operator on the Hilbert space, then the adjoint with respect to the scalar product of the Hilbert space. See, the subtle point is that the adjoint is defined for P pointwise, because we use the fact that the elements of P are functions. But in the scalar product, the adjoint has its own definition, which is this. So you have to check that the two coincide. Of course, usually they do not. But in fact, the condition is that the adjoint in the two set. Now, what you conclude for this? In Hilbert space, you conclude they are equal. In Hilbert space, you conclude that they are equal up to a zero norm vector. But this is sufficient to prove what we need, which is positivity. Because if I have a positive polynomial, you see, I will, let me explain what is the reason. Okay. The reasoning is this. We want to prove that if I give the scalar product, then this scalar product defines a state. The obvious candidate, which is the state. I define a linear functional phi of P by definition to be the identity times P times the identity. So here I consider the fact that P is an algebra, so it acts on itself by multiplication. Okay? So the obvious candidate for the state associated to the scalar product is this one. And I have to prove that this is obviously linear functional, because scalar product is linear in the second variable and anti-linear in the first. So I have to prove that it is phi of 1 is equal to 1, but this is obvious, because this is my condition, necessary condition I put in the assumptions of the theorem. So I have only to prove positivity, because it's a linear function. By definition, a state is a positive linear function such that phi of 1 equals 1, and I have to prove positivity. Positivity follows because if I have to prove that that phi of an element, a positive element of the star algebra, because this P belongs to the polynomial algebra. I want to prove positivity on the polynomial algebra. And we know that in the sense of polynomial algebra, I must have that this must be positive. But by my definition of phi, this is equal to 1 R star R1. But because of this identity, I know that up to vector of norm 0, but a vector of norm 0 doesn't alter the scalar product, because the scalar product, everything is 0 by the Schwarz inequality. So up to a vector of norm 0, I can write that this is equal to R daga R1, and this is the norm of R1 squared, which is positive. Okay. So we have proved that phi of 1 is 1 and the state is positive. Okay? You understand? So the second assumption played a fundamental role in this crucial step, this identity.
And you're using Cauchy-Schwarz to say that you're using Cauchy-Schwarz
to eliminate the zero norm vectors.
Cross is same.
Because the scalar product of a zero norm vector for any vector is identically zero by Cauchy-Schwarz. See, so we have now proved that this state is, and this condition will be very much, this proposition will be very important in the basic theorem of orthogonal polynomial, what we will call the reconstruction theorem. I was hoping, I hope I can show you the reconstruction theorem in one dimension. I don't know. We will see. Okay, now the reconstruction theorem in the theory of orthogonal polynomial is known under the name of the Favart lemma. But the Favart lemma was in one dimension. There are many, how to say, in the literature, you will find many claims that there is analog of Favart lemma, but this is not true. And in the future lecture, we will discuss at length this point, and you understand why. So now we have from now on, when I speak of the scalar, I will indifferently speak of scalar product on P, or scalar product on P, or pre-scalar product on P, or state, because I give for granted that my scalar product comes from state, so that this is a necessary and sufficient condition, plus normalization is satisfied. Okay? So we use interchange. Once we have the scalar product, so we have the pre-Hilbert space structure, we have P with its scalar product. Okay? And what is the standard procedure in the theory of orthogonal polynomial? You take the monomials, x to the power n, and you orthogonalize, not orthonormalize. That is why, because I want to keep the vectors of 0 now. I will try to explain later on. We will discuss this. So we get an orthogonal family of polynomials, which is the orthogonalization of monomials. Okay? Orthogonalization is an algebraic procedure, so you can do it easily. If you have a vector of norm 0, they give 0 contribution. So no essential problem. You can Gram-Schmidt orthogonalization works. So you have a sequence, and these are called the orthogonal, more precisely the phi orthogonal polynomial. These are called the phi orthogonal polynomials. Okay. Now there is a very famous relation that I don't want to prove, because we will prove directly in multi-dimension, and it's useless to repeat twice the proof. But this is the famous Jacobi relation, which is the